Okay, welcome everybody. My name is Jan Pollmann, again from the Ruhr University in Bochum. I work in the field of application for shape memory alloys, and I'm going to begin with giving you some background on my research project. Together with a lot of other universities all around Germany, which you can see here, we're working at a research project called Small Machine Tools for Small Work Pieces. Which means, I don't know really if you know, in the field of micro machining, the tools used are almost as big as the tools used for macro machining. And that's the thing that we think is kind of wrong, and we want to rectify this. In this research project, all these universities work at developing innovative actuation and tool modules for configurable modular machine tool. So what we want to achieve is micro machining tool which you can fit on your desktop. What we're hoping to do is having a cube with the dimensions of 400 millimeters, which can house all these different actuation and tool modules. And we want to be able to manufacture parts with dimensions of 10 by 10 millimeters. Wide range of parts and materials, of course. The advantages we hope to achieve is high flexibility in placement because it's such a small system. Fewer parts and less materials needed, so hopefully we're gonna be a little bit cheaper than the machines used right now. And as I said, there are 11 universities all around Germany working on this. In my project, I'm building axis based out of SMA actuators, and we started with a very basic concept. We have one SMA actuator consisting of a housing, a bolt, and the SMA wire actuator. And when actuated, the wire pushes the bolt out of the housing and thereby creates a displacement. Combined, in this picture, there are 4 actuators to just increase the displacement you can achieve. We have resetting springs for all the actuators together, just to keep the individual actuator kind of simple and cost effective. And with these axis components, you can just combine them to to build a 3-axis machine. That's our basic concept. Then developed it further and achieved this prototype. We have here 5 SMA actuators. I'll go into detail for them just in a second. They just running on a linear guide on individual slats. And the displacement they create together is then transferred to this top plate here, on which the next axis can be mounted. The resetting springs for all these actuators is actually underneath here. You can't see it in this picture, but it's just, as I said before in the concept slide, is just one resetting spring for all these actuators. The individual actuator, it's kind of hard to see here on the beamer, but you have here just a part which is machined out, just you can put the SMA wire in, and if it's actuated, this bolt just gets pushed out of the housing. And we have a top plate here, and here actually little ceramic plates, which we put at the ends here and crimp the SMA wire on the other side of the ceramic plate, just to keep it in place in the actuator. I think it's kind of obvious how this works. In the cold state, the SMA wire is here, just you can see in the blue line, and if we activate it, it shortens and so pushes out the bolt out of the housing. What you can achieve by that is actually bigger displacement and in a smaller space, and a little bit more wire force we can use. What we do for our actuators is a smart flex wire, either 0.3 or 0.4 millimeters of diameter. Our whole experimental setup right now is one SMA axis. It's our X axis. Then we have an interface used to mount the next axis. This is actually developed by our colleagues in Hamburg. And for the y-axis, we have this block of aluminum. It's not very effective, but we're just doing right now our experiments with the one axis. So this is just a dummy to simulate the weight and dimension. And then another interface, and then we developed an SMA-powered clamping device to hold the workpiece in place. And here we just have a regular air-powered milling tool. So our problem now with this setup, if you're doing milling operations, and for example you want to drill a hole, you have to maintain one position for a prolonged amount of time. And you might know that actuating SMA wires for a longer amount of time, they don't really like that so much. So we were trying to figure out a way how to keep these axes in place without powering all our SMA wires all the time. And yeah, then we started developing this latching device or braking device. As you can see here, it just fits in the axis and at the place where this brace was before, which transferred the displacement from the last actuator to the top plate here. We replaced that with the latching device, which consists of these brake pads here, which just press on to the bottom of the axis assembly. And here you see our prototype. How that works in detail is, again, you see the brake pads. Those are pushed down to the bottom of the axis assembly via regular springs. And in the middle of these springs, there's an SMA wire running from here. Hopefully you can see it over to here, and which is capable to pull the brake pad up. And if the brake pad is in the topmost position, there's a lock bar here. It's kind of hard to see, I guess, but this lock bar just it's also spring powered. It gets pushed into the brake pad actuator here and keeps it at the top position. And the lock bar again is controlled with an SMA wire, so the brake is bistable, so if you want to keep it in the down or in the up position, you never have to power the SMA wires. If you want to release the brake, so stop the actuator, stop the whole axis, you power the lock bar actuator, pull the lock bar out of the spring assembly, the brake pad gets pushed down by the regular spring, and you can achieve your braking force right there. What we normally do with our axes, just a setup without the braking device, we have kind of a path we pre-program, or reference path, and see how the deviation is between our reference path and the measured output of the axis. Keep in mind we have to do micro machining, so the deviation should be kind of small. What we achieved so far is a deviation of average minus 5 microns from the desired position, and standard deviation of 18 microns. That's what the whole axis can do with the 5 individual actuators. And on the next slide, we have the results with the integrated latching device. As you can see, there we had to use another scale for the deviation here because of the most extreme position of the axis, so at around 28 millimeters, the brake pad actually hit the bottom plate of the axis assembly. It was just a minor problem with the design, which I couldn't fix before coming here. So the important part of the deviation is the first and the last part here. This will be corrected as soon as I get back. So the latching device actually, except for this part, doesn't have any effect on the accuracy of our axes. And most importantly, what we try to achieve to keep the axis in place. We put a load of 20 newtons on the axis while the latching device was engaged, and we found there was 0.1 millimeter displacement under load and a 0.01 millimeter residual displacement after removing the load. That sounds kind of much, because I was talking about microns before. But keep in mind, when doing micromachining, the forces which are generated are normally around 1 Newton or under that. And as you can see in this graph here, with the force on the axis is under 1 Newton, you of course have a lot less displacement, residual or under load. So that's kind of feasible for this application. To conclude, the requirements we had for this latching device were met with our experiments. We can prevent the prolonged activation of the SMA wires in the axis by using this device. The control of the device is very simple and can be easily integrated in our existing control setup, because you just have to send a small current impulse through either the spring actuator or the lock bar actuator. What we have to do, of course, is to correct the design flaw I talked about earlier. And what we can do to better this design is to increase the properties of the friction between the bottom of the axis assembly and the brake pad. Right now it's just actually aluminum on aluminum, so not very good. We have some ideas for that, and the stiffness of the axis itself, of the whole assembly, will be increased in the next prototype to limit the influence of the assembly on the displacement you saw earlier. So, thanks for your attention, and I'll be open for questions now.